Hello and welcome to today's webinar, How Does Your PCB Stack Up? Tips for Creating the Perfect Stack Up the First Time. My name again is Sarah Krieger and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. If you have any questions throughout the webinar, please type them in the question panel as they come up. We will have representatives ready to answer your questions directly during the webinar. With that being said, I want to thank you all for joining us today for today's webinar and introduce to you our presenters. Matthew Hearns and Sue Frederick. Matthew is an electrical engineer from Canada and has been with EMA as an application engineer since 2003 and as the application engineer team leader since 2018. At EMA, he specializes in design side issues pertaining to part management, circuit simulation, signal integrity, and power integrity, but is conservative in all facets of the ECAD design. Sue has worked with the Cadence tool for over 25 years, both as a PCB designer and application engineer. Prior to joining EMA, she worked in post-sales customer support at Cadence, focusing on the front-to-back OrCAD, Allegro, and PCB SI flows. Matthew will start off the webinar, followed by a demonstration from Sue. Assuming we have time at the end, we will field some questions and a formal Q&A. Thank you for your attention, and now over to you, Matthew.
All right, thank you, Sarah. So the agenda for today, this is what we're going to be covering in slides, and then we'll be passing it off, as Sarah said, to Sue for a demonstration of some of these features as well. So the agenda is design cycle impact. Then we're going to talk about the importance of collaboration, which is a really big deal, making sure you communicate well with your manufacturing house. We'll talk about the composition of a stack up, materials you can use, how to pick your layer count, how to figure out what your impedance is going to be, and also embedding components. So that's what we're going to talk about today. First off, the impact on your design cycle of your stack up. You want to make sure you pick a good stack up, and stack up really is a fine balance of cost versus functionality. Make sure you want to keep your costs down and get the functionality that you need. As you constantly are shrinking your board, you're running out of space, you have to think vertical and start putting more layers in there, but that comes with consequences. And we want to learn a little bit about what those consequences are and how we can make sure to minimize their impact. And also communicating with your manufacturer, again, helps us eliminate unpredictable schedules and communication delays over materials that might not be available or might be long back ordered or too expensive and you have to change your mind on something else. Don't want to interrupt our workflow. We want to be able to pick our stack up and proceed with that and not pay anything extra for that. And again, not have any delays due to manufacturing, and that all comes down to, again, communication. This is really going to be a key theme for the webinar today, so I wanted to mention it first right off the top, and that's the importance of collaboration. And this is working with your board manufacturer. So once you've picked someone who you would like to have make your board for you, you need to be in close communication with them for all types of decisions that you are going to need to make about your board. Lots of them are around cost implications, so what type of vias you can use, what type of core materials you want to use, what your stack up count is going to be, if you're going to use blind and buried vias, if you're going to do back drilling, if you're going to do embedded components, if you're going to do rigid flex. All those types of things have cost implications, and you want to make sure to minimize the cost while maximizing the amount of productivity that you're going to be getting from your board. Also, manufacturability. Some things that you might want to have be made for you simply might not be able to be physically made. So beyond it potentially costing more money for something you want, some things just might not be able to happen. And you need to be in contact with your board manufacturer to determine what those things are and make sure you can figure out different ways around those potential problems. Board manufacturer is going to be critical for finding out how to meet your impedances that you want to achieve. Normally, you'll be able to get it in a ballpark, and then your board manufacturer will really dial it in to get to the very specific impedance value that you're looking for. And you want to limit your DFM errors, so the design for manufacturability errors. You want to make sure those go down so that you don't have any manufacturability problems. And I believe we did a webinar on that previously. You can check on that one and see what we can all do around that. Constraints. Constraints are things that you're then going to get from your board house. Your board house is going to say your spacing has to be this, your trace width has to be this, and a variety of other constraints that your board house is going to give you based on the Stackup that you've chosen and the processes that they use to achieve the results that you want. Also, another thing is lead time for uncommon materials or processes. If you want to use some fancy materials that they don't necessarily have in stock, those are going to have to be ordered, and you want to make sure that that doesn't push your schedule back. So collaboration with your board manufacturer is key and something that is going to be mentioned throughout this webinar. All right, so what is a Stackup first? The PCB Stackup plays a central part in your overall performance, and you can kind of think of it like a lasagna or like a burger, but you're starting to put things together and you just want to have more layers for more options. Now, why do you need more than just one layer? Often because of board constraints. So things are getting, so your board ultimately needs to fit in some space often that's so small that you need more vertical space. You're just out of space on the top layer or the top and the bottom layers. Components are taking up everything there. Now you need different ways of making the connections you want on the inside layers. What does our Stackup generally look like? So we saw in the poll question at the beginning, you have a couple options for Stackup. You have single layer, you have dual layer, or you have multi-layer. Multi-layer is going to be anything bigger than 2. In the poll question that we saw the majority of the people on the call today are in between the greater than 2 and 10. And there's a few of you that are doing even boards larger than 10. How does it work when we build up a multi-layer Stackup? What's all going on there? What happens is you take plane pair core materials, and you see that kind of on the left-hand side of the graphic. Plane pair core is coppers on the outside of a core on the inside, a dielectric core. And that the manufacturing house is going to have. They're going to have plane pair cores. And if you want multiple layers, then you start sandwiching those together. You start sandwiching those plane pair cores together and constructing larger multi-layer Stackups up to however many layers you want to use. The balancing. Balancing is another important thing, and part of manufacturability. You always want your boards to be balanced, meaning that from the center, from your center layer, looking outwards, down and up, you want everything to be a mirror image. You want it to be matched going out from that. And it needs to be symmetrical from the center out for balancing. The reason for that is because you want to avoid warpage. And we're going to see another slide on that in a little bit. But if you have more material or more copper on the north side of the center line than you do the south side, it can encourage warpage and problems with your board. You want them to be flat. A poorly designed Stackup can degrade your electrical performance, your power delivery, and your manufacturability. We're going to talk about those a little bit more, but you don't want to decrease those things if you can avoid it. Solder mask can have an effect as well too. So we're going to be kind of popping in and mentioning a few things that can be important for really high-speed designs. This is one of those things that on extremely high-speed designs you might want to consider not using. So solder mask is often avoided when sensitive circuitry is involved because of its lossy behavior at high frequencies and some other problems as well. But it can have a wide range of dielectric constants, meaning that your dielectric material is going to be kind of unpredictable, which has an ultimate effect on the impedance of your trace, which is really critical in high-speed signals. What we're seeing here on the right-hand side, that graph, we're seeing the insertion loss per inch for bare material compared to solder mask. You can see when there's solder mask on, that's the green trace, you get a little bit more losses than you would without. So in some cases, it makes sense to just use bare copper instead of putting the solder mask on that. Another type of Stackup you can have is flex. So rigid is your regular board, but then you can have flex merged in with that. Flex is that flex cable. The reason you want that is for wiring that works, meaning you can have a more solid connection. You're not relying on connectors quite as much anymore. Everything's right tied into the board core. And it can help for miniaturization and weight reduction. 3D packaging can also be useful. You can pack things a little bit more tightly together and just fewer interconnects and points of potential failure overall. That board Stackup then looks like this. You have your core material running through the entire board, including the flex, and those then are built up differently beyond the core material than the rigid portion is, and are hopefully going to be bendable for you. So that's the goal of having the rigid and the flex together. We're not going to spend a ton of time again in this webinar talking about rigid flex boards. That we did another webinar on in the past, and you can refer to that one as well for a more detailed look at rigid flex. The first thing you're often going to do in determining how your Stackup needs to look is you're going to get information from your mechanical CAD team, and they're going to tell you it's going to go in this structure, and therefore it needs to be this big, and you might even have height requirements and mounting constraint areas where you can't put any electrical components. And that outline that the MCAD team is going to give you is going to be the start of how you determine how many layers you want to use in your board, or you need to use in your board. That's going to be one of the key restrictions that you're going to get to narrow it down. Now that we know a little bit about the Stackup and kind of how it starts, let's talk about some available materials that we're using in Stackups today. The most common dielectric material is one called FR4. It's a woven glass epoxy, and it is, as I said, the most common. So that's the most commonly used dielectric material. It delivers good performance versus cost. It's got good manufacturability and durability and overall good electrical properties. So it's a good material overall. And there are other materials that you could use if you'd like to, but this one is a good general purpose dielectric that you can use. Different dielectric materials, when you're talking high speed again, like we were previously, when you have high speed traces, you want to again make sure your losses are minimal. You don't want to lose your signal quality as you pass your signal from one location to another on your board. And you want to potentially consider using other dielectrics in this case. So if you want high-speed design work and you're looking for better quality signal from one point to another, you might want to consider using different materials. So there's a number that are used in the industry, and a number of different trademarks. G-Tech and Rogers are some that are commonly used in this space, and they offer better attenuation, again, as shown before. Same type of graph here. So losses per inch in red is FR4. You get a little bit more signal loss than you do if you use a higher quality material that you see in green there. So less signal loss, higher signal quality overall, which is something you want. You also get an increase in heat resistance. So this has an added benefit with some of those better insulation materials, that you have better heat resistance. Polyimide is the dielectric material that's used in rigid flex designs. So this is the one that's bendable. It's an insulation material that you can also bend freely, and that's why it's used commonly in rigid flex design. So excellent bendability across a wide variety of temperatures, and it, like the other core materials that we saw on the previous slide, is available under several different trademarks that you can purchase that type of material from. For electrical connections, so we saw the dielectrics. There's the FR4, there's some more expensive materials, and there's polyimide for the flex. For the electrical, the conductivity that we want to make connections with, copper is really the core material that you're going to use. And it's got a great balance, similar to FR4, of performance, versus cost. So the cost of it is relatively cheap compared to other conductive metals, and the performance of it is quite good. So normally copper is well used, and there are some cases where you might want to consider using other plating materials like nickel or gold, but generally the core of your conductivity is done in copper. And that's just because it works really well and the cost is the most affordable. How thick is that copper? So the thickness of that copper can vary depending on your needs, and that's going to come with some trade-offs. So how thick your copper should be. Usually it's measured in ounces. So if you ask for a 1 ounce copper thickness, that doesn't necessarily make sense in terms of thickness. But what that actually means, one ounce of copper is considered to be pressed flat over 1 square foot, and that gives you 1.37 mils or approximately 37 micrometers of thickness. So meaning that if you ask for 1 ounce copper for your conductive layer, that's going to be equivalent to 35 micrometers. If you double that up and say, actually, I want 2 ounces, that's going to be double the thickness. If you half that and say, I want ½ ounce copper, then that is going to be approximately half of the thickness. And just for a scale to give you a sense of how thick or thin that is, household aluminum foil is about 0.63 mils or approximately half ounce copper, the same thickness as that. So just to give you a sense of how thick or potentially thin that is a ½ ounce. So as I said, if you do need thicker conductive material, 2 ounce, 3 ounce, 4 ounce, to carry more current, that's normally why you're going to want to do that while maintaining a certain temperature, you can get thicker conductive materials. And back to the almost very first slide I talked about, this is something you'll certainly want to talk with your manufacturing house about, whether they can source these thicker conductive materials and the cost associated with that. So if thicker materials isn't an option, maybe just more layers of this material. So if you need a thicker ground to carry more current and not increase your temperature too much, but you can always throw additional layers in as well. That's another option. From the IPC spec has some good data on how the cross-section of your conductive material against the amps that are flowing through it, how that relates to temperature rise. So given a certain cross-section of copper and a certain amount of amperes flowing through that, what is the expected temperature rise that you're expecting to see? And you want to make sure that you fit that within your requirements and pick a adequate type of copper for that. And note also from the equations here that it's going to be different for the outer layers compared to the internal layers. So there is some difference there in the current carrying capacity of your traces depending on if they're on an outer layer or an internal layer. The copper, when it's etched using the acids in the manufacturing process, this can cause some issues. It doesn't just go perfectly straight down normally. There is some trapezoidal effect where it takes away more at some area compared to another. And depending on the process and the manufacturer, that can often be at the bottom. It could be at the top as well too, but you do want to be careful of this and have that conversation with your manufacturer. And that will normally lead you to width restrictions, saying that you can have a 5 mil trace. A 4 mil trace might cost more money because they have to use a different process. A 3 mil, maybe more, perhaps they're not even able to do it. So these are the types of conversations you want to have to make sure that the trace that you lay down stays in place and doesn't corrode itself right away and you have nothing left of that trace. So some manufacturability issues, those normally come in the form of constraints from your manufacturer telling you how thick that trace needs to be able to remain present after the process is complete. Etch balancing is another thing. We talked about layer balancing near the beginning, where we were saying from the center out, you need to have the same thing going down as you do going up. Another type of balancing you need is layer balancing. So on your plane pairs, I was talking about the plane pairs with the dielectric and the copper on either side of that. It's not a great idea to etch the majority of the copper away from one side of that and leave the majority of copper on the other side of that. The reason, again, is warpage. It would cause that plane pair to warp as it has much less copper on one layer than it does the other. So that's something you want to avoid, just excessive etching from one layer and not enough etching on the other layer. You want to make sure they're relatively balanced. And the way to do that is to just leave the rest of the copper on the layer. In this case, we see layer 1 in the upper left-hand corner where it's all etched away except for the traces themselves. And the correct way of doing that for balancing sake is to leave the copper on, just etch the outside of the traces so that they're isolated, but leave the remainder of the copper on there. And that's normally a good idea anyway for grounding and shielding. It normally doesn't hurt too much. Surface roughness is also something that we need to consider potentially when determining things like impedances, and sometimes the different materials that you could use have different surface roughnesses, and they could have an adverse effect on your impedance at the end of the day. So that's something, again, you'll want to consider and be in contact with your manufacturing house about if impedance is a very strict restriction. Okay, picking our layer count that we have. Some of the key factors in picking how many layers need to ultimately end up in our board is from, first off, I said a few slides ago, the MCAD. The MCAD team is going to pass you a board outline most likely with a few component placements and a few regions where you can't do anything. And that's going to give you a good indication of how much additional space you're going to need. And the only way you usually have to grow is vertically. So that's going to be indicated here in your layer count picking. Another thing that's going to be a big indicator is your BGAs and how you're able to escape from those BGAs. So the signals in the middle need to be escaped out of your BGA pattern so you can actually use them in your board. And that can be determined by your layer count. So you might need more layers to be able to get all these signals out to different places. And you may even have to consider different via strategies. So if you're using blind and buried vias, that might give you more accessibility into the middle, and also what type of vias you can use and how big they can be. And that again depends on your layer stack up. And we'll talk about that in a bit when we get to aspect ratio as well. But lots of things to consider and all kind of tie together when we're considering how many layers to use in our design. Your SI group is also going to have some feedback for you. So they're going to have some requirements on the integrity of the power signals. They're going to want lots of power planes and ground planes sandwiched in your board, and that just helps reduce EMI and give nice return paths for the signals to travel back as well. They might also ask for things like back drilling. And back drilling you see in the screenshot there, if you're unfamiliar, it's where you have a via, and the via is not, it maybe comes from the top, a signal comes from the top and goes to an internal layer. And the remainder of that via barrel after the internal layer, when it goes off, effectively acts like a stub in terms of signal integrity. And if you remove that, that can improve the signal quality. So that is something that can be done and adds additional costs. So it's a bit of a trade-off. Is the signal quality important enough to warrant the cost, or is it not? And that's a decision that you can make. But back drilling and using blind and buried vias can be beneficial for signal integrity quality most of the time. But again, it's the trade-off with cost. The input from your power group as well, they're going to have some requirements on your Stackup as well. They're also going to want probably lots of power and ground layers, and they're probably going to want thick copper on those so that they have fewer thermal issues to worry about. So the thickness of the copper and the number of planes, they want to make sure that that's adequate for the current load that they're expecting on the board. And those material selections and the amount of material that they have is going to have a major effect on the temperature rise and making sure that's within their design specifications. So the power group wants to make sure that there's adequate path for the current to flow to power the devices and doesn't generate too much heat that's ultimately going to cause problems. So another trade-off with performance versus cost you need to have a conversation with your manufacturer about. How about split planes? Can you split planes up and put different power or trace signals on your power plane? Can you share it, or does it all need to be one? And really, lots of times you're going to need to share those power planes. For power signals, especially BGA, like we see in this picture here, has lots of different power plane requirements, and it's going to need to be fed those different powers from different places. So that creates a lot of splits in our power plane, and that can lead to greater signal integrity complexity and just problems even getting out of that BGA. And signal quality can be hindered, as if you have a trace traveling over any of those gaps, that can cause impedance discontinuity issues and reflections and overall general problems. So split planes are usually a necessity because you normally can't have a layer for every single power that you have, and you often don't quite need that much. But where there's splits, they cause potential problems as well. So how many power planes to use? The answer is kind of as many as you can afford. As many as you can afford to have in your board stack-up is good, but the more the merrier. Generally, half or fewer of your overall electrical layers will be power ground. So if you have a 10-layer board, you're normally going to have half, which would be 5, but probably not an odd number. So you're going to have four power ground layers most likely. And of those 4, normally half are going to be power, half are going to be ground. So 2 grounds and 2 powers. That's normally how stack-ups are done. There are exceptions, but that would be probably the norm. And power and ground are often right next to each other. They don't have to be right next to each other, but they often are, and that helps, again, reduce your EMI, lower impedance, and minimize loop currents as well in your board. So those are some guidelines for picking your layer count. Another thing to consider is the board thickness to via size, and this is your aspect ratio. So if you have a really thick board, that makes it hard to drill a really small hole. And the reason it's hard is because plating that really small hole is hard when it's really thick. So hole sizes that are small compared to the board thickness can result in problematic via plating. And the larger the aspect ratio, the more difficult it is to get that. So if you have a really thick board, you can't have a really small via anymore. And most board manufacturers should be able to achieve aspect ratios of 6:1. That's pretty standard. Most board houses can fit that, and they'll start charging you more as that gets smaller and smaller. So if you have, for example, a 30 mil thick board and you want to make a 5 mil via, that should be fine. But if you want to start going down to 4 and 3 on that same thickness, that is going to be problematic and possibly more expensive. All right, let's move on to impedances and talk about those for a few minutes. So how do we determine what the impedance is? And again, how do we work with our board manufacturer to get the impedance just right? So a microstrip, first off, we'll just define what a microstrip is. A microstrip is a trace routed on an external layer. So you only have 2 of those external layers at most. You have a top and a bottom, and every other layer where signals travel are going to be strip lines. So strip lines are internal layers, and they're often routed between 2 power layers. And strip line is usually desired by the signal integrity group for having less EMI radiation. So those 2 power layers that strip line is in between are going to neutralize a lot of the radiated emission that trace is going to generate, and really cap that off so that those radiations don't get out and you meet the requirements for minimal radiation. So that's something that signal integrity groups are often going to want to have you do, is put those critical signals inside the board somewhere instead of having them run on top. How is the impedance calculated? There's really only 3 or 4 things, I think 4 things that play any part in calculating the impedance. One is the dielectric constant. And we talked about the dielectrics, that was the FR4 and the more fancy materials that we offer. So the dielectric constant is going to play a big part in what the impedance of your trace is ultimately going to be. Beyond that, things are mostly physical in terms of what's the width of my signal. The width of my signal is going to have a big effect. The distance to the return path layer, the thickness and the width of my trace. So those four things are going to have a pretty big effect. And there's some equations that you can pull up. So if you do want to calculate the impedance, you can pull up equations. And I think these were an IPC spec where I got these from. Most people are probably not going to do that. There's a wide range of online calculators that you can use as well to determine your impedance based on the board stack up that you have and the materials that you're using and the thicknesses and the geometries is probably more common. Differential pairs are another thing where impedance really is important. You want to make sure you maintain some impedance that you would like to meet. And again, it's going to take into account the dielectric material, the width and the thickness, and now the spacing as well too. So the spacing now comes into play, the distance between those two traces. You can have microstrip differential pairs, you can have strip line differential pairs, that's the second graphic, or you can have broadside coupled, which is another type of differential pair where you have two signals traveling vertically on top of each other. So you have one on one layer, and on the layer below, which is another signal layer, you have the other end of your differential pair traveling on that. So those are a couple different options that you have for differential pairs, and you can calculate the impedance for any of those. Some other high-speed constraints or potential problems you need to be concerned about are things like the fiber weave effect. So the FR4 is like a glass fiber weave, and the weave can begin to have problematic effects on your signal quality as you get into the higher speed signals. And what we see in this graphic is one trace that's right on top of the weave and one that's going across all the gaps. And those can have different impedances in reality just because of the makeup of the dielectric material that they're on top of. So that can be problematic, and that can be compensated for by routing your signals on a little bit off grid, off angle, I guess would be the better way of saying that. So if you route at not 0 and 90 degrees, if you route at different angles, that's something that can be minimized. The effect of this can be minimized because you're not traveling right along the weave. So sometimes people do that at 10 degrees or some other degree that's just not quite 0, not quite 90, and just a little bit off angle so you don't just travel along the weave or the gaps like that. Materials in your stack-up are also frequency dependent. And we've talked about frequency dependence a lot, and especially at higher frequencies, this can become problematic. So the material that you used has frequency behavior, and it changes. So the impedance is therefore going to be different at different frequencies, depending on the types of materials that you use. So that needs to be considered as well. You have other options for figuring out what your impedance is. You can use Field Solver, or you can use the equations that I showed you previously. Field Solvers are generally more accurate. They do use Maxwell's equations for electromagnetics and do generally a pretty good job of calculating your impedance. Ultimately, though, you need to take this data with a little bit of a grain of salt because you do need to talk to your manufacturer about their process and their techniques, and they'll be able to help you dial it in and get it to a very specific impedance. So if a specific impedance is something that's critical to you, do make sure you're speaking with your manufacturer about how to achieve that. All right. Embedding components. I don't have a lot of material on this. I just wanted to mention that this is something that people want to do sometimes in their stack-up as well, is just embedding components. If you're running out of space on the top and bottom layer, or you just want shorter connections at some points, it becomes necessary to embed your components and actually put them inside your stack-up. So this is, again, something that comes at a cost, and it can be a pretty high cost depending on exactly what you're trying to do, but embedding those components into your board is something that can be beneficial overall, and again, something that can be costly as well. But in some cases, it's just something you have to do to be able to fit everything in the confined space that you have. All right, some goals to aim for. Here's 5 takeaways that I have for multi-layer boards, signal layers should always be adjacent to power planes, meaning that you should not have 3 signal layers in a row because that middle signal layer would not be adjacent to a power plane. So don't have 3 signal layers in a row, have 2 at maximum, and that way they're always adjacent to at least 1 power plane. Signal layers should be coupled closely to their power plane. So you want those connections, the distance to be as close as you possibly can. And same thing for power and ground planes. You want them coupled together as closely as possible. The routing of high-speed signals through buried layers between planes to contain radiation. So this was what I was mentioning about those high-speed signals. You want to put those high-speed signals on internal layers so that their radiation is contained within the power planes that are surrounding it. And multiple ground planes to lower impedance and radiation as well too. So you want low impedance, low radiation to get out of your board. All right, Sue is going to be talking about different Stackup creation templates that you can use, some different materials that could be available, and how to measure some impedances in the board tool. So let me pass it over to Sue, and she'll take over from here.
Okay, thanks, Matthew. I'm just going to show a demonstration here of the Stackup editor in PCB Editor. As Matthew had mentioned several times, when you're designing a board, it's very important to work closely with the board manufacturer to see what requirements they might have for minimum trace widths, trace spacing, number of layers that they can build, and for the right price. Knowing this information up front can avoid any kind of potential design rework down the road. The manufacturer also knows what materials they might have in stock, and this can help keep the cost of the board down as well. So by default, when you bring up the Stackup editor in a new board, it's going to open up with 2 layers. You can come in here and you can add layers to the Stackup. You can add layer pairs, layers above, and things like that. Optionally, you can import either a cross-section technology file or an IPC 2581 cross-section file. Here I'm importing an 8-layer technology file. So in this Stackup, you can see that the impedance on each of the layers is close to 50 ohms, which might be what you're looking for, but impedance shouldn't be the only consideration when designing the Stackup. There are also signal integrity and power integrity concerns that may need to be addressed. So when designing the multi-layer board, ask yourself the following questions, the following 5 questions that Matthew had mentioned. First, are the signal layers adjacent to the planes? This Stackup, you can see that the signal layers are, the outer layers have a plane next to them, and the internal layers are embedded between the reference layers. Next, are the internal routing layers for high-speed signals? Here you have internal routing layers, and they are between the planes so they can be used for your high-speed signals. This will help minimize the noise. Now, are the signal layers closely coupled to the planes to help provide a good return path for your high-speed signals? Here the outer layers are closely coupled, but the internal layers aren't really as closely coupled to the plane layers. So this could cause some issues down the road. Are there multiple ground planes? Here there are two ground planes, so that's satisfied. This will help to lower the reference plane impedance of the board and reduce radiation. And then lastly, are the ground and power planes closely coupled to increase the interplane capacitance? The plane pair in the middle of the board is not really tightly coupled, so it could be an issue here with your power delivery. Now, an even better 8-layer Stackup might have 2 power and ground plane layers to help with your power delivery, and these plane layers can be tightly coupled. The high-speed signal layers are at the center of the board. Notice that both of these Stackups have both been symmetrical around the center line. So this isn't a requirement, but it's recommended, as Matthew had said, to reduce the warpage of the board when it's manufactured. So in this Stackup, you can see that a thinner core is used between the plane layers to increase the interplane capacitance and help reduce the effects of EMI. A thicker core is used between the internal signal layers, resulting in less coupling and reduced crosstalk. So one of the signal layers can be routed horizontally. The other one can have routes that are routed vertically, which will also help to reduce the effects of the crosstalk on these layers. Now, since the outer layers are microstrip and only reference a single plane, the impedance here is higher than on the internal layers. So the strip line layers have two reference planes, which can be used to better control the impedance. Now, these impedance values in here, this is an impedance calculator that you can use in the cross-section editor. So if you want a 50 ohm impedance on your outer layer, you can just click in the cell, type in 50 ohm impedance, and you can see the line width that's required to meet this 50 ohm impedance. Say you don't want an 8.7 mil line width, let's try an 8.5 mil line width. To see what impedance we get by entering in 8.5, you can see that we're still around the 50 ohm impedance that we're trying to meet. Now, a thing to note here is that the impedance calculator is actually using a field solver. It's not using equations. So using the field solver, it's going to take all your different physical characteristics that you've set up here in your Stackup to generate the impedance. So it's more accurate than if you were using the equations. You can also change the dielectric constant on your internal layers and see an effect on the impedances on all of the layers. And you may notice here that the dielectric constant is being set for dielectric layers as well as conductor layers. This is because when the board is fabricated and the prepreg is pushed between the layers, that prepreg is going to be floating around the traces on the signal layers. So the value of the dielectric constant on the conductor layers is actually the dielectric constant of that prepreg that is between the traces. This is definitely going to be changing your impedance values in the board, so it's a little more accurate to define the dielectric constant on the conductor layers as well as the dielectric layers. You can see that these should be set up correct. If you put a dielectric constant of 1, for example, on these internal layers, it's going to change your impedance by quite a bit. So it won't be as accurate as if you have the dielectric constant of the prepreg that's surrounding the traces. Now this Stackup has all your signal and plane layers defined, but there is no solder mask defined on the external layers. So this is definitely going to be affecting the impedance on the outer layers. Right now, the dielectric constant on these outer layers is set to 1 because there's air that's surrounding the traces on the outer layers. But if we add in a solder mask layer above the top layer, we can go out to a mask layer file to define this solder mask. Say a layer function of solder mask, and then the material is solder mask. Add it into our Stackup. So now I have a solder mask on the top layer. You can see the thickness that was defined in that in the site level mask file, and the dielectric constant of 3.7 for this particular solder mask. So this has changed the impedance now of this top layer. But since we now have a solder mask over the top layer, this dielectric of the top layer needs to change to represent what the solder mask dielectric is. So changing it to 3.7 to match is going to change the impedance down to just over 48 ohms. If we want to get back up to 50 ohms, you can type in 50, and it'll calculate the trace width that's needed to get that 50 ohms on the outer layers. Now, if you decide that you need more routing layers than what you can get with the 8-layer board, you don't want to remove any of your power or ground planes. You should really be using a 10-layer board instead. And a 10-layer board can be manufactured in the 62 mil thickness that an 8-layer board can as well. So this 10-layer Stackup is good because of the tight coupling of the signal and the return planes, the shielding of the high-speed stairs, the existence of multiple ground planes, as well as a tightly coupled power and ground plane pair at the center of the board. And just by default, a 10-layer board is going to have tighter coupling just because there's 2 extra layers in there. So by routing the high-speed signals on the internal layers, the planes on layers 2 and 9 are going to provide a shielding for these signal traces. And also the signals on layers 3 and 4 are isolated from the signals on layers 7 and 8 by the center power plane pair. So this will help to minimize your coupling and crosstalk between the signals on each of these plane pairs. And once again, you can route horizontally on one of the layers and vertically on the other layer to help with the crosstalk as well. So similar to calculating the single-ended impedance, there is also a differential impedance calculator in the cross-section editor. Since the outside layers do not have an adjacent layer, signal layer on them, you can only select an edge-coupled differential pair on this layer. So edge-coupled, the differential pair is routed on the same layer. Now here, let's say we're trying to achieve a 100 ohm impedance on the outer layer. If you click in the differential impedance cell, you're presented with a box where you can enter the impedance that you want and choose to select if you want to recalculate the line spacing or the line width. So right now we have a line width of 5 mils and a line spacing of 6 mils that gets us 91 ohms. So if I want 100 ohms, I want to recalculate the line spacing that's required for a 5 mil line width. We can see that it's 10.4 mils spacing. That'll get us about to 100 ohms. So I might want to have a 4 mil trace width on the outer layers. By changing that, you can see that the differential impedance has changed to 109 ohms. Getting this back down to 100 ohms, we want to see what spacing is required for a 4 mil trace width. So we'll choose the line spacing again, and once again it'll recalculate, and you'll see for a 4 mil line width, you have a 6 mil spacing to achieve that differential impedance. So the same thing can be done on the internal layers, where you can set it up for edge or broadside coupled, changing the impedance to 100 ohms. You might want to have it recalculate the line width based on the spacing you have. So here's just go back and forth and determine what your spacing and trace widths need to be to achieve this impedance. Now, if you notice in all of the stack-ups that I've shown, the materials being used are just copper and FR4, so nothing too fancy, just standard materials that are used quite a bit in PCB board. If you use the pull down here, you can see a whole list of materials that you can select from. Now, these materials are located in a file that's called materials.dat. A default set of conductor and dielectric materials are located in this file up in the installation directory. But this file can be edited and moved around so that you can use it for all the designers in your company. If you have other materials that you'd like to add to the file, you can. This can be done using the materials editor. And once you bring this up, you can see this in use column shows which materials in the materials.dat file are being used in the Stackup currently. So here air, copper, and FR4 are all being used because that's what we saw in the Stackup. And this is where you can add different materials. You can right click on a material and say add new material. When it comes in, it's going to default to a type of dielectric. This is because it comes in with 0 electrical conductivity. In order to change the type, you can just change the conductivity to a number other than 0. And now we have a conductor layer. You can change the material name, my material, and then change any other parameters that you want to in here. So it's easy enough to add any layer and any materials into this materials.dat file. Once we apply it, it's going to ask if you want to save the materials.dat that's already there. And then going back into the Stackup form, now for a conductor layer, since I added a conductor, I can come down here and I can choose my material that I just added to the materials file. So up until now, I've been talking about just Stackups for traditional PCBs. Rigid flex Stackups can easily be created in the cross-section editor. This is showing a rigid flex design that has multiple zones defined for the rigid and the flex areas of the board. Each zone is associated with a Stackup that is defined in the cross-section editor. So this primary, flex 1, rigid 2, these are all Stackup names that cross-section editor. So looking at the Stackups in here, you can see that the all Stackups is used to enter your conductor and non-conductor layers for all of the different Stackups. As stackups are added, the layers can be checked and unchecked depending on which layers are needed in that area of the board. So for example, the primary rigid section of the board, you won't be needing your flex layer. So these are unchecked for your primary section. Similarly, your flex areas of the board do not use the paste mask top or the solder mask top. So they're going to be unchecked in these sections. Now the primary stack-up represents the largest number of conductor layers and is considered the default stack-up in the design. Only non-conductor layers can be toggled on and off in the primary stack-up. In rigid flex designs, the primary stack-up is most likely the rigid stack-up. Additional stack-ups can be created to support the flex sections and the lower count rigid sections over here. Now this is already set up with the stack-ups in it. I'm not going to go into how to set up the stack-ups because this is covered in a different webinar that was put on recently. So in addition to the All Stack-Ups tab, each stack-up has its own individual tab. The layers can't be added and deleted here, but the physical characteristics can be changed. You can change your material types in here, the widths, and once again you have your impedance calculator that can be used in each of these stack-ups. And notice that as I'm changing and going between the different tabs, there's a view over on the right that's showing the stack-up for each individual stack-up. If you look at the All Stack-Ups tab, you can see it's showing every stack-up that you have designed in the stack-up editor. This cross-section chart can be floated if you want to see a larger version of it. You can see how each layer is showing here as it's checked and unchecked in the stack-up editor. So this is representative of what is being checked in here. So as you've seen, when deciding on a stack-up, there really aren't any hard, fast rules as to how many layers constitute the best stack-up for high-speed designs. The decision is going to be based on cost and on materials and the needs of the design. Work very closely with the board fabricator as well as mechanical engineers, electrical and power engineers to determine the best stack-up that's going to fit the board that you need to design. So that concludes the live demo portion of the webinar. I'm going to pass this back to Matthew.
So just to summarize some of the things that we talked about today, with a good stack-up, we can minimize our manufacturing, what's going to cost money, what's necessary, what might not be, and figure out what additional add-ons we would like to use to get the behavior that we want to in our board. We can find out and streamline schedules and make sure that we're talking to our board house early, make sure we have communication with them in place so that we can see the materials are all going to be available and time is going to be set aside for them to work on our designs. We want to minimize those communication delays and ultimately improve time to market, make sure our product arrives on time. I did want to do a small plug for the Hitchhiker's Guide to PCB Design. That is a book that we've created in the past, and Chapter 7, the whole of Chapter 7 is on Stackup. So that's available for free. You can just Google Hitchhiker's Guide to PCB Design, and it'll be one of the first things that comes up. So feel free to get that downloaded. It's a free download. You can get a PDF copy of it. I believe it's available or soon to be available as a paper book if you want to read from paper as well.
All righty, thank you, Matthew and Sue. It looks like we have a few more questions coming in, but that's all the time that we have for today. However, if anyone has questions that we weren't able to address during the webinar, we will be following up with you on an individual basis. Thank you for taking the time to join us today. Bye-bye.